Hello, this is Unlock Circuits 18EC42. We are discussing Module 1 and Lecture 1 today, which corresponds to the BJT biasing. First question which arises is, why do we need biasing at all? So the purpose of biasing is to establish a constant collector DC current. Constant collector DC current. Or constant DC collector current for the BJT. Indirectly, it just means fixing the quiescent operating point. That means what is the value of IC for a particular value of VBE as well as VCE, VBE and correspondingly the VCE. So this value should be kept constant. So to have it constant, we should have the biased collector current should be calculable and it should be predictable. And also it should be insensitive to variation in temperature, and even though there are large variations in beta. That just means that even if the temperature changes, the value of the DC collector current should be constant. Also, if there is device replacement, which will provide large variation in beta, because the beta value will be anywhere between 50 to 200. Okay, even though there are variations in beta, the DC collector current should remain constant. Further to that, the fixing of the operating point should be in such a way that we should be able to get maximum output signal swing in the IC-EVCE plane. IC-EVCE plane just means at the output over here, at the output over here. Okay, so we should be able to get maximum output signal swing over here. Now there are two bad biasing schemes. There are two bad biasing schemes. One of that is shown over here. Please note that there is no emitter resistance here. We have a potential divider network, a collector resistance, and the transistor, no RE, no RE. So now we can just replace, what you call in the analysis, we will have the value over here. It will be straight away the value of, VCC, and this will just give you the base current which is flowing over here, base current which is flowing over here. So this value of RB will be straight away corresponding to the parallel combination of RB1 and RB2. RB1 and RB2. So this is the first case where we have the fixed VBE, where we have the fixed VBE with a voltage divider network, and correspondingly we see that the relationship between the IC and VBE is shown over here, and this is exponential, and this just gives us that even though there are small changes in VBE, there will be large changes in the quiescent collector current, quiescent collector current. So this I with a small capital C is the quiescent collector current, and I capital C is the DC collector current. So even though there are variations in VBE, IC should not change. IC should not change. But here, because it is exponential, we see that when VBE changes, IC also changes. So this is a bad biasing scheme. Another biasing scheme is fixing the IB. This is fixing VBE. This is fixing IB. And that is done by putting this, single resistor RB. Single resistor RB. So in this case, the value of IB will be VCC minus VBE by RB. VCC minus VBE by RB. The value of VBE will be in general 0.7 volts. 0.7 volts. Once we know the IB, then we can find the IC as IC into beta IB. IC into beta IB. So the value of the IC will be beta into this total value, beta into total value. If there is variation in beta due to device replacement, we see that the value of IC is also going to vary. So there will be large changes in the value of IC when beta changes, and correspondingly large change in VC. Hence, again, this corresponds to a bad biasing scheme. In both the cases, we will not have constant DC collector current when there is variation in temperature and when there is a device replacement. So we go for other techniques which will keep the DC collector current constant or stabilize the DC collector current. So one of the techniques is the classical discrete circuit bias arrangement, where the RE resistance is introduced compared to the figure over here. Okay, we are introducing RE over here. So this gives us the classical discrete circuit bias arrangement, and now we'll try to find the Thevenin's equivalent voltage for this potential divider network looking in this direction, and that will give us the voltage between this and this looking in this direction, and that will be the current flowing through this here will give us VCC divided by R1 plus R2. If you multiply that with R2, then we will get the voltage across R2, and that will be the voltage which over here. VBB will be VCC into R2 divided by R1 plus R2. Or VBB is equal to R2 divided by R1 plus R2 into VCC. Or VBB is equal to VCC by R1 plus R2 into R2. Either way, it is just the same. And also the Thevenin's equivalent resistance looking in this direction will be the parallel combination of these two, because the VCC will go to ground at that time. Therefore, the parallel combination of that will just give us R1 into R2 divided by R1 plus R2, and that is the resistor which is there over here. So we are trying to replace this by the Thevenin's equivalent, and this is kept as it is. So the Thevenin's equivalent voltage here, Thevenin's equivalent resistance here, and this is the expression got from here, and this is the expression which is got from here. So having found the equivalent circuit over here, now we can find the value, the what you call equation which just corresponds to the input loop equation, that is VBB minus IB into RB. VBB minus IB into RB is equal to VBE plus IERE. VBE plus IERE, and the value of IB is nothing but IE divided by beta plus 1. IB is nothing but IE by beta plus 1. Thus, we'll get this equation. VBB minus IE divided by 1 plus beta into RB is equal to VBE plus IERE. So now we can take the IE terms on one side and the other term on the other side, that is VBE this side and this IE term on this side, and then we can try to find the expression for IE, and that will give us VBB minus VBE divided by RE plus RB divided by 1 plus beta. So when will, now this IE is almost the same as IC, because IB is comparatively much lesser than IE. So under that condition, we can see what will be the value of when will this become stable. If VBB is very much greater than VBE, if this voltage is much greater than VBE, and if this resistor is much greater than this, we'll have IE is approximately equal to IC equal to VBB by RE. So the condition is VBB should be much greater than this, RE should be much greater than this. So under those conditions, we make the IE and hence IC insensitive to temperature and the beta variations. It will become constant, VCC divided by VCC divided by the value which just corresponds to RE. VCC is constant, RE is constant. Whereas VBE is variable with the temperature, and this resistor RB by beta plus 1 will vary with the beta value corresponding to transistor. So if the transistor is replaced, then we might have a different value of beta, and hence the value of RB and beta plus RB divided by beta plus 1 also will be different. So both these conditions should be considered. So first condition is condition for IE insensitive to small variation in VBE, that is 0.7 volts, will give us, and this will be the case under this condition. We see that the limits are the highest value of VBB should be 1/3, and the lower value of VCB will be also 1/3, plus the voltage across RC should be also 1/3. So it just means that over here, okay, over here, the value of the what you call VBB here will be 1/3. The voltage here is 1/3. The voltage here is 1/3, and the voltage between this and this is 1/3, and the voltage between this and this will be 1/3 of VCC. Voltage from here to here 1/3. Voltage from here to here 1/3. Voltage from here to the ground also 1/3. Now this value is very small, 0.7. Hence, we can also consider that this voltage is 1/3, this voltage is 1/3, and this voltage is 1/3, and that is what is generally considered. And that is what is written over here. VBB is, or you can say VBB or VE is 1/3 of VCC. VCE or VCB is 1/3 of VCC. ICRC should be 1/3 of VCC. So this is the rule of thumb which we will consider for design of the biasing circuit. Further, the condition for IE to be insensitive to variation in beta, which is there over here, IRE is greater than RB divided by beta plus 1. So we should have very small, RE to be much larger than RB. RB should be much small. RB should be much small. And also we should have lower Rin and higher current drain from the power supply. Higher current drain IC should be much larger from the power supply. That means the value of the current which is flowing here should be much larger. So that means IR1 and IR2 should be equal to 0.1 of IE. 0.1 of IE, that is almost the value of IR1 and IR2 should be 0.1 of IE, and IR1 and IR2 should be much larger than IB. So if IR1 and IR2 are much larger than IB, then we see that the IB will become less dependent on the beta. IBB will become less dependent on beta. Current flowing through this, the two resistors should be much larger than the base current over here. So ultimately we see that the value, the RE is going to provide negative feedback, and the negative feedback gives us the stabilization in the bias current. So VB is mainly determined by R1 and R2, and the constant that is if IE, and it will become constant. If IE increases, then VE also increases. If IE increases, if the value of IE increases, then the value of VE also increases. If VE increases, then the value of VBE decreases, because this should remain constant here. This voltage remains constant. If IE increases, VE increases. If V increases, because this is constant here, voltage across resistance, the VBE value should decrease. If VB decreases, then correspondingly the value of the IC and IE are also going to decrease. And that is because there is a relationship between IC and VBE, which we have already written over here, which will be similar to the relation which is over here. So thus, bringing back the value of IC and IE to the normal one. So here we have IE increase, here we have IE decrease. So that means if you increase IE, again there will be a decrease. So that means stability. That just gives us the stability. The second method for biasing is the collector to base bias feedback resistor. We provide a collector to base bias feedback resistor. We provide here a collector to base feedback resistor, and if that is the biasing method, then that also is going to give you the stability. So the analysis of that is shown over here. You can see that this is IC and this is IB, and IC comes here and IB will come here. So both IC and IB will join and that will become IE. So we know very well IE is equal to IC plus IB. Further, from this current IEC is going from the IC is going from this point and IB is going also from this point. So the current which is flowing here will be IC plus IB equal to IE, which is flowing through RC. So now we can try to write the equation for VCC. VCC is equal to IE RC, this IE into RC. Then we can come on this side, IB RB, voltage across this. VCC is equal to voltage across this plus voltage across this plus voltage across this. That is IERC plus IBRB plus VBE. And IB is nothing but IE divided by beta plus 1. Again, that is the standard equation. IB is nothing but IE divided by beta plus 1. So now again, rearranging the terms, that is IE, you can take common here, VB, you take on this side, IE value will become VCC minus VB divided by RC plus RB divided by beta plus 1. So again, we have two conditions, that is VCC should be much greater than VBE and RC should be much greater than RB divided by beta plus 1. So under that condition, IE will be not just VCC by RC, but here used VBE also. However, if you feel that VCC should be much greater than VBE, you can just write VCC by RC. Same, conditions continue over here. That is, VBE is dependent upon temperature, and if that is negligible, then we'll get stability in IE. Also, if the device is replaced, then beta also will change. If RC is much larger than this quantity over here, then you can just neglect it, and the variation of that also gets neglected. So on the whole, we can say that RB provides negative feedback. So the allowable negative signal swing and the collector is determined by RB, and that is the limit on the RB. So IE should be insensitive to the variations of beta, and also temperature dependence, which is there in VB, also is negligible. So VCB will be IBRB, VCB will be IB into RB, and IBRB is IE RB divided by beta plus 1. One of the most important method of biasing is the constant current source, but however, this is out of the scope of our syllabus. You will be studying more of this in the VLSI design. Please remember that in all the integrated circuits, we use constant current source rather than the methods which are used earlier. So here you are using passive devices, resistors are there. In the earlier also you have the passive devices over here, whereas here if you see there are very few passive devices. If you take this circuit over here, there are no passive devices over here, only one resistor is there, and that is the one which corresponds to this, and that is the constant current source biasing, which is generally used in the integrated circuits, ICs. So with this, we come to the end of the lecture 1. Thank you, one and all.